time, and so we thought we should do some presentations about Erlang. So and thanks for tonight's venue and feedcast sponsor, DEK Technologies. As you see, their beautiful offices here. Hope you enjoy the food and drinks, and it's provided by DEK Technology. So tonight we're going to have two presentations. I'm going to do a quick introduction, and then the first one will be introduction to Erlang into an organization like DEK. Magnus, the manager of DEK, will tell you more about how to bring a technology as Erlang into an organization like this. And now we're going to have a coffee break, some feedback, some mingle. After that, we have Erlang co-inventor Joe Armstrong to talk about his recent hobby project. And after that, we have some mingle. And just before the event starts, I'd like to say something about another event. It's called Go to Stockholm. The event is in May. It's a conference, but there's going to be a free launch party in 1st of March. It's full of developers. It's also a meetup. There you can see Elixir's inventor, Jose Berlin, is coming to Stockholm. The event is also a meetup. It's free. It's 1st of March, and you're welcome to come here. Just in the advertisement for our meetup organizer. Yeah, the first presentation introducing Erlang to organization by DEK, and the second one 6:30 by Joe Armstrong. He's going to be talking about Swift and the hobby project he's been doing recently. And throughout the meetup, we're going to take some photos. Please relax and smile. And we're going to post all the pictures on the meetup group. And if you want, so you can see if you have any comments or feedback, please talk to us. If you want to take some pictures down, also it's okay. And thanks for tonight's sponsor. And we prepared a bit of a surprising gift. We had prepared two gifts. They are glasses from the previous Erlang user conference. They look like this. Unfortunately, we only have 26, and it's plenty of people tonight. So we thought those of you can stay until the end can take one of these home, and a limited edition from EUC. All right. Please enjoy the meetup. And please welcome, give it up to the first question.
So, welcome to DEK. Really proud to finally host the meetup. I think we've been talking about this for a year probably. Then you guys came to us and asked us if we wanted to host a meetup. So we were really, oh yeah, we want to do that actually. And then we said like, let's do it once we move, because we were sitting in Norgegatan 2 before. It's like the outskirts of Kista. So close to Husby you can come without being in Husby. And it was a really old office. Now we're really happy to be in our new office. Anyway, I will like how to introduce Erlang into an organization successfully. Let's see. Okay. Good. So my name is Magnus Sedlacek. I'm the general manager of DEK Sweden. This story about the Erlang and DEK is kind of tied to me actually. I'll present it through the presentation. Yeah. So let's get started. So in 2008 then, we got 2 requests for Erlang developers at Ericsson actually. And this is what we heard about Erlang in 2008. It's maybe not the right, but this is the perception that was thought like. The perception of Erlang, it's impossible to learn for C, C++, C#, Java developers. I'm not stating it's right, this is what we heard. From everyone. It's an obscure little language. It's used by Ericsson, maybe not. Some people even told us that Erlang has been banned for a while in Ericsson. And the people that develop Erlang usually do it in underground projects, and then all of a sudden it's a working product. This is what we heard. And there were an obscure little small company in Stockholm, also a startup company at that time, called Creditor, which is today Klarna, that used Erlang. It's like, and even if Ericsson uses Erlang, there's not so many assignments within Erlang. Why would you want to go with Erlang? It's going to be impossible. It's A, impossible for your people to learn. B, there's no assignments. But anyway, we started. We were actually two guys. It was me and another guy called Daniel, who today works at Klarna actually. So we started working with Erlang. And then, show you the next. So instead of boring you with every year, we just made a graph of the amount of engineers we have working with Erlang. And you can see it's like started out with me and Daniel in 2008, and then it's kind of tagged along. We got a little bit more assignments. We got some assignments in. We work mainly with Ericsson. We got some assignments within IMS, and then some assignments within Dura, radio department in Ericsson. And then up until 2012, then something actually happened quite drastically in 2013. That's when we went from like 10 developers to 39 developers over more or less a quarter or two, actually. I'll come to that in the next slide. But as you can see, we have grown, and we also want to highlight that we have actually brought, I think there are other companies actually in Vietnam that also uses Erlang, but there are quite a few. We've been at least training around 25 guys in Vietnam in Erlang, also in Ho Chi Minh City. So we've actually been there and brought it there also. And in 2010, I worked in Ericsson department that at that time started, they called it the second site in Shanghai. So I was also part of bringing some Erlang and Erlang testing specifically to Shanghai, actually. So, 2013, in Q2 2013, then DEK got more Erlang assignments. We went from 2 teams to 5 teams, from 10 engineers to 39 engineers. So, so we decided that we need to develop our own DEK internal Erlang course, because if we're going to teach this many people, before we had like one more guy, we brought them in, they did some self-studies, someone went to courses, somebody did self-studies. We decided, well, we're going to do this on like a massive scale now, not just one guy, 2 guys in a team, where we can bring them in, mentorship them, teach them, and then off they go. So we decided to develop our own DEK, like the internal Erlang course actually. So in July 2013, 3 guys from our office in Sweden flew down to Ho Chi Minh City, and we trained 12 engineers in Vietnam in Erlang. And actually much more, because they pretty much didn't know anything. That's not fair, but they knew some things. So we taught them everything around Scrum, Agile, Ericsson, SVG, how we work, how ClearCase works, how Ericsson documentation systems work, and a little bit of Erlang also. Yes. And then we formed mixed teams with experienced and newbies and Swedes and Vietnamese. We thought that was a good way to get forward, and also to always have some kind of experience in every team, so everybody always could ask an expert, have someone with an expert knowledge within Erlang close to them. Then, 2015, last year, we decided to take the next step, so we formed an internal DEK Erlang community. And at the same time, we hired Don, and I think Don and the Erlang community are one-to-one. We developed our own, more like advanced Erlang course, and we started to give it to our DEK engineers. I think most people have worked with Erlang. They worked with it in an Ericsson context. They thought that, well, this maybe is not the latest and greatest stuff that you can do with Erlang. There's been a lot of development since they started to develop the product we're working on. So let's take the more advanced concepts. We also offset 10% of the engineers hired for training. Use it as they want to use it. There was a huge request for this, like, can we get 10%? Can we get more time to like develop ourselves? And then we did that. And then we tried to start an internal Erlang project. We fumbled a bit. We didn't really know what to do and what to start and where to like, what should we do? Build a CV database? Maybe that's not so fun. We should do something. And then I haven't mentioned it in the slides here, but actually we found out, we got an idea, or I got an idea, an old idea I had back in 2010, that we should build like a system tests load generator in Erlang, because the language is perfectly designed for that actually. So we decided to try it out as an internal project, mostly to people to learn more actually. Yeah. Now we'll come like to what we learned then. How to start. I think that what we didn't do to all the new people, this went to, you remember back in 2008 we said that we heard that it's impossible to learn Erlang, and then yet we learned Erlang, so we didn't tell people that Erlang, don't mention that Erlang is any different than any other language. Don't go to people and say it's a functional language, it's not been used, don't do all this bad. When we went to Vietnam, we didn't say anything. We just went there and said, this is how the language works, this is how we work in Erlang. And they just learned. There were no, they didn't have any kind of, oh, it's impossible, I don't understand functional language, I have to think differently. There was nothing like that. Also for what we did, like, luckily, we didn't think of that at the time, but went that identify the key engineers and get them to embrace Erlang in your organization. I mean, that's key here. So it doesn't come this obscure little part of your company that everybody thinks is underground and they're working the other way. And then with a lot of debate internally here, like how should you do this? Should you start like giving courses or self-study? I'd say adjust it to the engineer that's going to do it. Some people love to do self-study, some people love to go to courses. Depends on the individual. This is very tied to our history here. So, how it grow then? Well, when we went to 10 engineers, I think you can go, if you have 6 to 8 experienced Erlang engineers, then you can ramp it up massively if you like, dependent on the complexity of the product you're working on. We train new engineers by using our own course. Maybe that's a good idea if you want to ramp it up massively. Also, like form mixed teams with beginners and experienced engineers, so you don't leave people behind. And then, as always, like within the team, like do pair programming, mode programming, mentorship, possible for less experienced engineers. This is what we learned. Then what? This is where we are actually. Like we have continued to invest in our Erlang engineers' competence. We have started our own internal Erlang projects. We work with customer products more or less all the time, so we can't really tell anything what we're doing with their products, unfortunately. So, but if you do an internal project, then we can tell about that. So we started our own internal project to be able to like both do competence, but also show what we can do. And then, of course, you should host an Erlang meetup. That's it. Do you have any questions or thoughts or want to know more? Yeah?
So what this internal project is all about?
We're going to try to build a zip load generator to massively try to do system test or load test a node for a customer. They already have a load generator, which we think we can do much better actually. That's the thing. Just to show that actually if you do this, and we think with Erlang you can get much higher load with the same CPU. That's our, we are quite certain that we can do that actually. Yeah, any other questions or thoughts or?
Like, what's the typical breakdown of the team, like Swedes, Vietnamese people, seniors, juniors?
The typical breakdown in the beginning was 4 to 4. We had 4 Swedes and 4 Vietnamese. We had 2 experienced Swedes, 2, I don't know, started learning Erlang, and then we had 4 Vietnamese. The Vietnamese had all kind of backgrounds. Some had worked for a long time with C, C++. Some had worked with like Java, JavaScript, that type of PHP background. Yeah, that's it. If there's no more questions, I'm done. Thanks. Good. Then I think we have time for fika.
Now we have more time for a fika.
Yeah.
email script. Send to Apple. No. No, it's my Wi-Fi. No thanks. Oh, we're doing? Are we starting?
Let's start.
Yeah. Is that really right? Good evening. How should I start? I don't know how this is going to turn out at all. This is the first time I've ever talked about this. Bruce sent me a mail and said, would I like to talk to an Erlang user group? I said, yeah, sure. And he'd already written the abstract. Because I published a blog article about Swift. I was playing with Swift. And so I think he cut and pasted a bit of the thing and said, well, could I talk about that? And I said, yeah, sure. But I'll also talk about, I mean, that was 3 weeks ago, so I couldn't guarantee that would be what I was interested in 3 weeks' time. So well, I'll just kind of talk about whatever I happened to be doing at the time. So that's what I'm going to talk about. And so it's going to be a little bit of Swift and a lot of music. I hope that's all right, because I've been doing some real-time audio synthesis in Erlang. I used to work at Ericsson, but I became retired. So suddenly I don't go to any boring meetings anymore. So I've got a lot of time to do interesting things. And now I'm looking at some really difficult problems where the timing is really critical, where you really hear if things go wrong. And I'm working with a guy called Sam Aaron. He wrote this thing, Sonic Pi. Has anybody used Sonic Pi? It's a great application. Yeah, it's good. And what we want to do is, in Code Mesh in London, is get everybody with laptops to just open up their laptops and we'll tell them to download Sonic Pi. And we'll give a keynote, and then at a given thing, they will be an orchestra which we will start playing. And there'll all be different instruments and we'll get a conductor in it. And that, in order to do that, we have to solve some pretty tricky technical problems because the timing is much more difficult than telephony. You know, these stuff that Ericsson makes are trivial compared to orchestras. Orchestras are much more difficult, so this is a really cool problem. And if you make any mistakes, you really hear them. For example, when you change frequencies, you've got two sine waves and you change them, you've got to change them when they're passing through zero, not when they're not passing through zero, otherwise I hear a noise. So I've been sort of looking at that kind of stuff. It also happened, I bought a load of synthesizers years ago, and then I'd never had time to really get down to the nitty-gritty of how these damn things work. So I've got half a dozen synthesizers at home, including a Yamaha DX11, which I really hadn't figured out how to program. And so this kind of gave me an opportunity to combine music, which I like playing the piano, I like synthesizers and programming, a little bit of maths and physics. So this is kind of in the wash at the moment. So what I was trying to do with Swift, actually, was to replace some C codes that I've written. So I'm going to start. I've got a lot of little demos, but before I get onto that, I'll just have a little. I was going to do it in this order, just for fun. So, first of all, I've been learning. There are a couple of fantastic programs, Super Collider and Pure Data. Is anybody fans of the Super Collider? And Pure Data?
I find it, but I like not the whistle.
Right.
I like the coding.
Now, both of these programs have a learning. They don't have a learning curve. They have a learning cliff. So, like you know, the current view of how to learn stuff, it should be sort of easy for beginners like that, and then it should sort of gradually get more difficult. So with Super Collider and Pure Data, the learning curve is like that, and you're right down here, sort of shaking your head and bashed into this cliff, and I'm still sort of struggling to climb up this cliff. That's pretty tricky, but it's good fun. And I think my favourite quote comes from James McCartney, who wrote the Super Collider, and he said, the first software synthesizer I wrote was a graphical patching engine called Symphonics that generated samples with the ensonic mirror of sampling keyboard using a Macintosh computer. I attempted to sell the program but sold only 2 copies, one to Ivan, and I can't pronounce that name, Brim at Harvard, and another to Mark Polishuk. A business lesson I learned from this is not to sell products that requires the purchase of the purchaser to already own 2 niche products. You know, he owned a Symphonics synthesizer and he owned a Mac, and he wanted to program the two, and then he formed a company to sell this software product that was the intersection of these. You know, 2 people bought it. He thinks they're the only 2 people in the world who had both these things and wanted to program it. So this was a good business lesson. So now I'm going to do even worse. This is the intersection of music, mathematics, programming, and Swift and all that stuff. So I'm probably the only person on the planet who's interested in it. Right. So that was an aside. And then I'm just going to start with I wanted some acoustic things here. Just a little quiz to start with. So. These are local, so I found this, which was kind of fun. Good. No, that's a blog. Tails, teeth. No, there it is. That's the thing. So here's a little quiz. This is a way of doing a spectrogram of sound, which I found on the net. There's all this wonderful thing on the net. If you look, you'll find it. There you go. So that's a bird, right? And Take, I'm sure you could start a company here. You just take out your recorder and you tweet this, and you look at them. You see, it's about 2.8 kilohertz, and it's fairly regular. And on the blog, there's not my blog. This is not my stuff. Someone else's from this. You could identify. You could hold up your phone and it'd tell you what bird it is. Take should start a company with bird watchers, but he's not here. It's a multi-billion-dollar business, probably. It's great stuff. Here's another bird. Right, that's a different sort of bird. Right, now, I put up your hands if you recognise this. This isn't a bird. This is something else. What did I press? Can you press it? Sorry. What's that? How many know what bit of music that is? Only one person.
Which note is that?
No, I didn't ask which note it was. I asked which bit of music. How many? I'm not going to tell you yet. Don't say. How many people think you can possibly identify that? How many are absolutely certain? Oh, how many are not certain? Do you want to hear it again?
Yeah.
Right. You're certain you know what it is? Okay. Now just we'll see if you're right. I do this because my wife and I, we like Spotify. We sort of play things to each other, and I like to play that a little bit at the beginning, and I'm almost always right. So this one I was really right. So I did an experiment to see how much I need to hear in order to identify it. And this is the spectrum at the beginning of this, so you can see which notes are there. So if that's a bit difficult, let's make it easier to recognise. So there we are. Let's. How many know? How many can see from that? What zoom in a bit. Yeah. There you go. Oh, why isn't it zooming? I've got to get the mouse. There we. What? Oh, come on. There we go. So does that help? No, not really. Does this help if we play it? Hang on, let's see. It's a god-awful small affair. That helps. How many were right? Put their hands down. How many were right? How many who put their hands up and said they knew what it was were wrong? Okay, right, that's interesting. So we recognise music actually because of what's happening in the very, very early phases of the sound. Now, one of the things I've been trying to do for ages is transcribe popular music. So I sit at the piano and I just try to play along like that. Now, so that's very difficult, I think, because well, it's difficult for me because I can't hear all the notes that are being played. This is like a cook. I think you know, a good cook that tastes something that I can recognise sort of 3 or 4. My wife should go like, there's margarine in there, there's something, and you know, they can recognise 4 or 5 different flavours. I'm no good at that. I'm better at sounds. Now, most people could the easiest sound to recognise is the bass tone, the lowest tone, because there are no harmonics of that. The higher tones that you hear might be a harmonic of the bass tone, so you don't really know. So the easiest one to recognise is the bass tone. That's the one at the bottom. And if you're trained in, most people can recognise one note, the bass tone, reasonably accurately. Or they can say, if you play other notes, you'll hear these notes. But hearing two notes at the same time, that's pretty difficult. And hearing three notes, that's about what I can do. I can recognise three different tones in that first note. But the fourth note, that's difficult. That's really tough. There was a YouTube video of a little kid who was about 4 or 5, and he was playing music. He said, bang, bang, absolute pitch. 5-note, 6-note chords, boom, immediately. Wow, genius. Fantastic. So, in order to help me, this is a few years ago, I took the first, 100 milliseconds of life on Mars, put it through a spectrum analyzer, and looked at all the tones. And I found the missing fourth tone. So you could play the 3 notes. It didn't quite sound right. When I added this fourth one, it sounded right. But I only found it with a spectrum analyzer. Right. So I thought, yeah, I really like a program that just nipped through some music and helped me transcribe stuff. So that's actually what I wanted to write. So that was what I wanted to do. The other thing, I wanted to make music. And so let's go back here. So I thought, well, I wanted to make a a sort of thing like, you know, GarageBand. It's got all these things that play sound samples. So the first thing I looked at was sound, actually, waveforms, and how could I display them? I mean, what do I do with them? What is sound? Sound's just a list of integers. So music is just a function from, you know, it's a mathematical function. It has a type signature, f of composer equals a list of int. It's a really simple function. It's this type. The type of composer is a complex type, but the type of composer is bloody simple. It's just an integers. Right. So try to do that. So I thought I'd look at the start of some music. So wait a minute, let's look at this. I need to make a sample here. We'll select this. So, and then I thought, well, one thing I want to do is detect where I should put my frequency analysis on. It's called beat detection. Because your ear is so critically tuned into the start of music, you want to find out where it starts accurately. So, I thought I'd like visualize these waveforms. And there's 1 or 2 programs that do that. JavaScript, install in browser, the JavaScript. Unfortunately, they just show the way. They don't tell you the algebra or how they've done it, and the documentation doesn't say. So I had to reverse engineer these programs. So this one is just the average. I mean, we're taking 44,100 samples per second. So and this thing's 800 pixels wide. So you've got to do some averaging. So I was just taking a couple of hundred bins and averaging them. So this is just the average signal strength here. Most intensity plots don't look like that, so I've been messing around taking the squares of those and the logs and the derivatives just to see which looks better. I haven't made my mind up on that. And I figured out how you could cut and paste these buffers. So wait a minute, down here, yeah. So I need to do this. So I just thought, well, can I do this part of the problem that's cutting and pasting sound buffers? And the answer is yes. And so here was the first sample here. It's a god-awful small affair. And if I cut the last word here, we just hear this last bit here. Okay, so it's a god-awful small affair. And that comes at the beginning of this. You listen, you'll hear that at the. It's a god-awful small affair. And then the other affair there. So if we delay the second sample by a little bit, 2.4 seconds in fact, and then play it 4 times, we can get it like that. And then we just superimpose the two, and something went wrong there. Try again, sorry. And I wanted to sort of, on some of the audio tracks as we mixing things and adding them. And then the other thing I wanted to do was to put MIDI events in and artificial events in. And that's where Swift came in. Right, so I got about this far and I thought, oh God. So here I had, let's go back. A few years ago I wrote, let's see the loopa-doopa-doo, all this synth. Yeah, we'll go to here now. And does anybody know GarageBand on the Mac? I want to write something like that. And so I started writing Joe's band, and I wanted to hit the core audio stuff. And so I wrote this program, Joe's band, and so this is using the Mac's internal synthesizer, which is pretty crap actually, but it works. This is very British. This is it doesn't sound very good. It's not. But it's not too bad. But this is all the time. So this is you're hearing a real time effect. We don't hear any garbage collection delays or anything like that, which is really good. Because it'd be very embarrassing if we got garbage collection delays. We do hear that until we abort the program though. When we abort the program. Stop! What? Oh, thank you. Now, this is core audio. It uses these horrible things called NIFs. I hate NIFs with a passion that cannot be imagined. The NIFs are the creation of the devil and should never be used. And so, why don't I like NIFs? You fuck around with Erlang. You mess it up, and if you make a mistake in your NIF, you can crash Erlang, and that's not what you're supposed to do. You're supposed to have Erlang is supposed to run forever and not going to crash. If you put a NIF in, you'll fuck it up. It's even worse than that. The NIF I had to write for core audio. If we look at this thing here, is it a README somewhere? Yeah, it says no. Notes.md, yeah. It says, look at this, notes.md. It says, for compatibility with modern systems, Erlang must be built with 64-bit support. Build Erlang with configure -- enable Darwin 64-bit and then build as normal. So this isn't the sort of out-of-the-box Erlang you get. It's the one you have to use if you want to link with the core foundation libraries on the Mac, otherwise it doesn't work. And finding out how to link it was a pain in the rectum, which I wouldn't recommend anybody doing. And the code that does this, wait a moment, there's a NIF thing here, where is it? Oh yeah, macsynth.c. This is a NIF. And if you look at this stuff, this is Apple's idea of a bad joke. It's called core audio, and boy is it not fun, but we don't want to do this stuff. And then a programming language called Swift came along, and they said it was a functional language. I thought, I've heard of functional languages. Let's try and write some Swift to see if we can do the same thing. And so I wrote a blog. I played with Swift, and I wrote this Fun with Swift. Well, there you go. And that should come up. And I wrote this stuff. And actually, what got me into Swift was this program here. It's look at that. It's that long. I can almost get it on. If I make the window bigger, you'll see it. There you go. So that is a tiny bit of code. That's not much stuff. Now Swift, unlike Objective-C and all these other horrible languages, has got a REPL. I'm a great fan of a REPL, read, evaluate, print do. So, because when you're learning a language, you just type stuff in, hit character, and you see if you've got it right. So Swift's got a REPL, which makes it easy to learn. And you can run it outside of Xcode. Now Xcode is the biggest pile of fetid, steaming turds that the planet has ever seen. You know, nobody would voluntarily go into Xcode or Eclipse for that matter. Just keep out. Warning, dragons, dangerous. So the correct way to program is to Vmax and make files and bash scripts and nothing else, right? Possibly Git, although I'm not sure about that. I mean, it seems a lot of fuss. I mean, why would anybody want the old versions? You only ever want the latest version, don't you? Throw away all the old versions. Right, so here, let's see, if we go to Dropbox, experiments, no, it's a Dropbox, Joe Arms, where is it? No, it's Dropbox, experiments, Swift, MIDI, yeah. So I thought, well, is it here? Wait a moment. No. So I can't remember where I put things. Joe Arm. Posts, Swift. There you go. So here is this little browser.swift. Look at this, WC browser, here we are, browser.swift. This is browser.swift. It's a massive 34 lines of code, and you can run it in the REPL. So what happens when you run this? So you say Swift, browser.swift. Oh, look at this, it takes a little while. My goodness. Come on, there you go. Those 34 lines of code have created a web browser and gone to a web page at Apple and displayed it all and thought, wow, I can make a window with stuff in it without using Xcode. Wow. Glory be, thank the Lord for that. So, I wrote this blog article and thought, let's see if I can push it a bit. So I wrote these 7 experiments. They're documented here. So you actually run all of these Swift. What have we got? Let's say experiment. I don't know. I can't remember what these things do. Oh, what? This is great. Swift is one of these strongly typed languages which you cannot crash a code in, because it's really got this anal type system which makes sure it can't crash. Right. This is interesting, isn't it? How about Swift 5? It was working yesterday. Oh, here we are. So look, I made a window. And text changed. So I can actually make windows in Emacs with text and type make, and I don't need to go into Xcode. Thank you. And I can do music. So I'm sort of happy at this stage. Now I can get the internal synthesizer. They sound horrible. And then I thought, okay, so let's interface that to Erlang. But outside Erlang, so it's got to read TCP and everything, or UDP, or TCP. So I made a TCP socket thing that talks to the sound thing, all in Swift. And after I published this blog, an author of the book on Swift mailed me and said he'd like to help. And he sent me a copy of his book, and I started reading it, very kind of him. And so I thought, yeah, well, he can. And I kept on getting stuck, so I mailed him Swift. And, it's awful. Swift is dreadful. I mean, in order to get this stuff, just look, you can't imagine how horrible it is. Dropbox, experiments, Swift, MIDI. And the reason it's horrible is, let's see, like read MIDI keyboard.swift here, is you think you're doing all right until you got to write function my MIDI read prop packet list unsafe pointer of packet list unsafe mutable pointer of to a point. What's all this unsafe mutable pointer stuff? Oh, well, that's okay. So what in C would be star X? In Swift is 4 lines of uncomprehensible, unsafe mutable pointer to type of UX. And horrible. Sorry? In Swift. Yes, in Swift. I mean, it is just so. I mean, in order to do star star PC++, at one point I had to do this stuff here. I had to do let bytes mirror reflecting packet data option and dump string packet bytes of enumerate spawn string attribute. That's to do star PC++ in Swift. Okay, so I don't really like, I must say, what's the advantage of Swift? Well, the advantage is you get all the goodies in the Max libraries. That's it. I mean, what's the disadvantage? It's a horrible programming stuff. I mean, in a sense, it's okay. So Objective-C was better than C, in a way. So that, and Swift is kind of better than Objective-C, but that doesn't mean to say it's any good. It just means to say it's better than Objective-C. And if you want all the goodies in the Mac, then you have to do all this unsafe mutable pointer, this, that, and the other, and all that rubbish to make damn stuff work. I started looking at Swift when it's fairly early. It turned out to be a research project to read a file. Do you know how you read a file in Swift? Is there something like, in Erlang, read file? No. Well, there's something called read file. It's got an extra argument. It tells you what the encoding of the contents is. So, if it was in Erlang, it'd be like read file. This content encoding UTF-8. You've got to have this extra argument with content encoding UTF-8. There's no way you can guess that. You can't just read a damn file and get it in a blob, which God had intended. I mean, why won't you just read a file into a blob? Why do I need to know what it's encoded as? I just want a blob. Not in Swift. It doesn't work that way. Anyway, so then I was doing all right there, and I thought, wait a moment. If I write a TCP server that talks to core MIDI in Swift, why don't I write a TCP server in core MIDI that talks TCP in C? Because that's much easier. I thought, I'll dump all this malarkey. So I wrote that into the TCP. Sorry, I did a TCP to MIDI thing in C. Thank the Lord, because I've been converting C to Swift. And then I thought, hang on, I can run C on my machine, so I'll probably C. And C was much easier than Objective-C. And if you look at the core MIDI, it turns out it was written in the days before Objective-C was invented. And so core MIDI makes perfect sense in C. It's really nice. And in everything that they built on top of it, it's a complete mess. So you go back to C, it's easy. So I did that. And then I got talking to a guy called Sam Aaron, who'd written Sonic Pi. Here's Sonic Pi. Sonic Pi is an application written by Sam Aaron, and it does stuff. I mean, it's an educational thing which he's written, and he uses it for live performances. And I met him in the States, so we both giving talks at conferences, and he does live jamming and stuff, and so I thought, that'd be nice to control that from Erlang. And he said, yeah, well, it's really easy. You just send it OSC packets over UDP to port this, and then you can just send it with the program the wire, and it will just execute it. I said, well, that's cool. So this isn't documented anywhere. And so he told me how to do that. So I got that running pretty simply. And then he said, yeah, well, all these sound things use OSC. And I thought, what's that? It's Open Sound Control. So I found an Erlang Open Sound Control library. And I should say the Sonic Pi actually makes its music by talking to the super colliders. Super colliders making the sounds. Well, it's actually super collider synth that's making the sounds. And that's through OSC messages. So I thought I'd spy those messages and just reproduce them in Erlang. I found this OSC library and I wrote it all, and it didn't work. And I spent days scratching my bloody head. Oh, I'm sending all the right messages. Turned out that the library that some bloke put on the net was incorrect. And then it got like quick checks in and everything, but it's still wrong. So I really, So this was another lesson of life. Never use anybody else's life. Ever. Write them all yourself. Right. So I wrote them all myself. It worked first time. So then I made this OSC over UDP. And I thought, and I published a blog article about that. And then just to make sure it worked, I connected it to the Super Collider, to Sonic Pi, and to Pure Data, so I could play back-end things in any of these. And then I thought, okay, so now I can drop Swift. And I've got the back-end driver so I can talk to these things. So now I can go and do some music. So I found this synth stuff. I found this frequent spectrum analyzer stuff. I found that early on. And I started searching the net for, there's another article on my blog there about how we did it, but we'll go back, yeah. So, let me see, fun with Swift. Contacted by that, Sonic Pi using it live in my, I started using the Super Collider at Pure Data, 0.14, my head exploded. Your head will do you agree? Yeah, right. Your head is. These two programs, the Super Collider and Pure Data, are stunningly brilliant. And as you start searching the net, I found a very interesting phenomenon, and that is that bad stuff crowds out good stuff. This is why people say that you couldn't find anything good about Erlang. So, I'll get onto that. As I was searching for I stumbled by accident over web audio, and some people were doing web audio. So, no, you can't get them to use the Super Collider or anything like that, because everybody's doing web audio. All the cool kids on the block are doing web audio. So I started looking at web audio. And there I found something very strange. About half of all the examples that you find on the web describing web audio don't work. Right? And of course you don't know if it's you or them. And the reason for that is the web audio standards have changed with time. And people have published programs that probably did work 4 or 5 years ago. They don't work anymore. And of course, because they're 4 or 5 years old, there's a lot of links that point to them. And the new stuff that does work, there's no links that point to it. So the old bad stuff is crowding out the good stuff. And Google's algorithms are total crap because Google's algorithms say, well, lots of people point at this stuff and say, oh, this is good, it must be good, which is a really stupid way of would you work that way? A lot of people think that's good, therefore it must be good. That's Google's algorithm. Total rubbish. I couldn't find anything good. And then I found this. This is one of the first things that I had 3 or 4 aha experiences. And this is one of the first ones when I found this program here. And I'll have to go, let's see. Oh yeah, it's loading here. And there we go. Well, I thought it was quite nice. It gives me anyway. Now this is and this is open source, this thing. And I went to the website of the guy who'd done it. And there's like some little 13-year-old kid sort of reading it. He's far smaller than I am. I mean, how the hell has he done this? Now this actually doesn't use web audio. Well, it sort of uses web audio, but it uses something called it's a sample player. A sample player is one of the forms of synthesizers where you record each instrument. So with a piano, you've got like 66 notes, and every one is a little WAV file, a little MP3 file, and you're just scheduling these in. So that's called a wave player, a sample player. So this is the first sample player I found in JavaScript, and it runs in the browser, and it doesn't use that much CPU time, and the code is pretty short, so you can just read it. This is just a GUI and sample player and a database. But this little kid's got this thing, and there are hundreds of thousands of songs on it, and you can just kind of botanize in it and play them. It's all quite fun. I started reading the code. Oh my god, can you do that? But that wasn't the real aha feeling. Then I got to this here. And this blew the top of my head off. I mean, I went, oh my god! My god, this is fun. And you can't find this stuff on the net easily. So, here we go. Now this, well, no, let's connect it up to, why isn't it, oh, sorry, I have to connect, we are connected in. MIDI keys, it should see my, oh, I've got my nano key control. So I've got this little controller. So this is a Yamaha DX7 emulation in software. If you know what the Yamaha series synths look like, it doesn't actually look like that. It looks sort of like that, but it is an accurate software simulation. And the difficult thing about building a synthesizer is not the, well, two things. How the sound samples are actually generated, that's kind of tricky. But it's the parameterization of these things. There's hundreds of parameters to set, and if you get it wrong, it sounds crap. The nice thing about this is it takes the original ROMs that the Yamaha synth took, and you can just load them in, so you've got all your sound banks here, and we can have, I don't know, what do you want to, I don't know, a guitar or something like this. But I haven't got the tremolo on here, but I need a different sort of controller to do that. And then I found, hey, wait a moment, I can just start MIDI controllers. The browser understands MIDI controllers, and the signals just come in straight. So it's the only I mean, I've now got this thing with knobs on, and you just get signals going into the browser. It's the only hardware I know that seamlessly connects to the browser, so you can adjust things by twiddling knobs. And then I thought, yeah, this is really cool. Now, I've read a lot of beginners articles on how to connect up synthesizers and make oscillators and do all this stuff. And this sort of create oscillator, and so I grepped all this code. I had it on my disk. I grepped all this code, and I couldn't find it. It didn't appear to call any of these things. Instead, he called something called script processor. And I read the script processor code, and the script processor code was generating the sound samples in code. It wasn't using the built audio stuff. It was actually doing it in, for loops and while loops. And I mailed him and said, oh my God, you are generating the sound samples yourself in code. So he's got this function that's just spitting out these integers, given an input vector, which is how the DX thing is set up. And he said, yeah. And I'm like, bang! I've got to understand this stuff. So then I started looking into it, because remember I said I had a DX11. Now the DX11 had all these diagrams, and I never understood them. So the DX11 had, anybody do synths? And nobody? Oh dear. Yeah, I'm like talking to me. I knew I'd be talking to myself. So if you look on the Wikipedia, you'll see FM synthesis. It looks like this. It says we've got oscillator 1 like that, and something in here, and then we've got sort of something that's the modulation index, and we've got oscillator 2, and something comes out there, and then we've got an EG that goes in there, and that's their level 0 explanation of that. But if you don't understand what that diagram means, even Wikipedia is not much help. And then you have the thing, it's called algorithms, and you see things like this. This is about the simplest algorithm here. So this is called, it's called like algorithm 5. And it looks like that, or something. You're expected to know what that means. Well, I didn't know what it meant, and so I go like, so you look in the manuals, and it doesn't. So I searched and searched and searched. I found what it meant. This is a system of equations, but it's not obvious. So this thing here. So what is? It's based on the notion of FM modulation. So now there are two terminologies in simple. Some people call these things VFOs and LFOs. Other people call them carriers and modulators. They're the same thing, right? So in sync technology or in mathematics, you would say, okay, so you've got a sine wave here, sine of alpha t. That's just going to give you a sine wave. And FM modulation is when you add m sine beta t to that, and that's an FM modulated signal, and that's just a frequency here, or related to the frequency, and that's the high frequency component of the signal, which is normally called the carrier, or the high frequency HFC or HF, BFO or HF, I don't know. This is called the LFO, the low frequency oscillator. It's giving the low signal, and this is called the index of modulation. Modulation index. So, hey, I thought, well, I could write that in Erlang. That's really simple. Write in JavaScript. So let's do that. Now, what you put into this thing is you don't have to put a sine wave in. You can put no simple thing. You put a sine wave, a square wave, a triangular wave, or random numbers in, and you know, do you want a sine wave, or do you want a square wave, do you want a triangular wave? And that gives you quite a lot of sounds. Now, what do these diagrams mean? Well, they represent equations, because if I've got sort of x and y, that means that I could write that as sort of A equals oscillator 1 of some input, and then y is oscillator 2 of A1. So you just take the output of one and you pump it into the next. That's what we did with this sine wave. So, I mean, if you had the sine wave that looked like this, sine alpha t plus m sine beta t, that can be thought of as coming from a previous stage. So in fact, what these boxes do are a system of equations that do that. And then I thought, because it's a system of equations, we could rationalize that. And therefore you could use this asm.js, which is the very efficient form of JavaScript that is known to compile down to assembler. And I searched for that, and I found somebody who'd actually done that. So we actually turn a synthesizer, well, nobody's done that yet. I thought that would be what I could do, take the synthesizer definitions and partially evaluate them to produce a specialized program that produces that sound, because it'd be much more efficient. Oh, there's one more thing. Remember I said that sounds are very dependent on how the start of the sound is. So in fact, the standard FM oscillator, as it was first made, consists of an oscillator here that has the modulation index here, goes into a second oscillator, and that goes into a waveform generation, which you usually draw it like this. And that modulates that signal, and out comes that signal. And that is an amplitude profile for the sound. And when you press the on key, the note increases rather sharply. And then it starts decaying. So this is called attack, and this is called decay, and this is called sustain, and then it's called decay, I think, or something like that. And you can set times for this. In fact, the Yamaha doesn't have straight line kills like that. It has a lot of complex protocol. Now, a group of people who are mad have reverse engineered the chips on the Yamaha DX7 and have done bit exact simulations of the hardware. Right. So what I'm doing now is turning that into Erlang. So what I think is possible is we can write something like timidity. Oh, I showed you. Did I show you timidity? Now timidity. Here's timidity. Timidity is not bad actually. // ABC Sakharov Manonov. If we say timidity rack PC. So here's timidity. That's better than I can play, right? If I could play that one, I wouldn't be a programmer. But my computer can play it for me. So this isn't a wave. This is a synthesized waveform, which is expanding these equations in real time. But you could do it in Erlang. So I measured how fast Erlang can synthesize. Can it produce more than 44,100 samples per second? Yes, it can run almost double that rate. So we could potentially bit exact synchronize this and synthesize that. So I thought, I wonder if that would work. So I thought, I'll be nuts and try that. So, as I did the song, web audio play, web section averages. Oh yeah, so, yes. So here, well this is just a, now say you're impressed. Wow. That's a round trip from the browser to Erlang, producing a raw waveform, using some algorithm, sending it back to the browser and playing it. Thank you. A round of applause, please. So, I mean, it's a bit of a way to go to the Rachmaninoff, but I mean, we're almost there. Another week's hacking. Well, no, another year. And where have we got to now? We've got the Whopper Doppler, the design, the index play, well, visualizing stuff. I mean, just look at this. So I just showed them. This is another one that I found. I mean, this is sort of. We're not hooked up to the live keyboard here, but these sounds aren't bad. I've actually got the Moog sounds and the Hammond B3 sounds and things, and the CPU is running 3 or 4%. So, I mean, it's not. I don't think it's significantly worse than any other audio generator. So what happened is, this is really cool. The DX7 cost about 5,000 kroner when it came out, and now it's open source. Free software, you run in the browser. And even if it's not efficient enough, if we can't do a whole orchestra, we've just got to wait 10 years and we'll be able to synthesize an entire orchestra on a standard computer. So we're basically killing off the, it's not quite, the analog synth, when they do feedback are instantaneous, because at the speed of light, so the processor is actually not as good. Right, where have we got to? How long have I got? Right, so, where do I have to finish?
You don't have to.
I don't have to. Oh dear, shucks. Top design, index or visualize. What else could I show you here? Oh, stuff that works. Does it still work today? Oh yeah, I found some GUIs. Nah, never mind. Oh, they were great. I won't show you that the lights, but yeah, I found those. Amazing, that's amazing. Now, so this is all in a total mess. So what I'm trying to do is break down this problem into little atomic bits. Oh yeah, I did have FM synthesis. Trouble is I don't know where it is. Supercloud occurred data. I meant to put links in it. I was doing this today, but DX7 online synthesis. Fun with that. No. Oh yeah, this was some. This just shows you the web audio. Oh, no, it doesn't. And it's not. It's a bit bigger. So this is actually the. I mean that's. This I just made a file with a load of examples in, and this is just how you play stuff. You create an oscillator. You put a sawtooth on it and do this like this and it's too loud. Stop and then you can play and then you can mute it a bit and you can you can play a couple of pulses which are not very exciting. And then I wrote my own MIDI player which can only play 2 notes, but well, I mean that's I had to write a sequence. There's a very accurate clock sync thing there that you have to understand. And then I can record it. Oh yes, FM modulation. This is my FM modulation here. So this is actually sine alpha t plus m cos. Isn't it nice? Well, no, but I mean it is quite fun because if you go here, let me see, that was called web server web audio.html. If we do FM, play FM. I mean, there you go. There is. Let's move. Can you read that? Yeah. So there. So here we have FM. You create an oscillator, give the LFO frequency value 1 Hertz, give the high frequency 440 Hertz. Put the modulation index equal to the gain, which I'll put the gain equal to 50. And then just connect it all together and start. So if we change the gain or we change the modulation frequency, we could what could I do? Change the modulation, change the low frequency modulation value 0.5 like that. And then run it again, and you'll see we've got a much slower modulation now. But you probably want a bigger modulation. It turns out just the square wave to listen for what these things are, then you can do it. And you go, yeah, that's a square wave, or that's some white noise that's been put through a high-pass filter, that's been downshifted and compressed, and it's great. Because this gives you fantastic possibilities, because now we can invent our own sounds, and we can invent our own controller interfaces. So it'd be kind of cool to get a Raspberry Pi and a laser, or one of these Microsoft things that detect where your hands are, so that you can make your own, that plays stuff that you can think. The nice thing about computers, I can think music, but I can't perform it. I can think sounds, I can't create them, but I can tell my computer to do that, and it can create new sounds and it can create new music. So it's a fantastic thing. And I think I'll kind of stop there. Have any questions? Any questions? Anybody want to build synths?
So what was the problem with driving MIDI core from the
Sorry?
Erlang shell?
What was the...
Why not to drive MIDI core from the Erlang shell in the first place and have your music at the REPL of the Erlang itself?
Oh, I can do that. I didn't like having NIFs in Erlang.
But you don't have to have NIF, you can have other facilities.
Oh yeah, I do. Yes, you can. Sure. Yes.
Oh, okay.
Yeah, I mean, it will have all that stuff. I mean, now I just make an architecture where well, OSC is a fantastic protocol. I kind of dismissed it because it's got this C, open sound control. You can control anything with it. And it's like one of these binary, it's not one of these stupid things like JSON or XML. It's sensible. Because it comes, ASM1 is like tag length value. But there are no keys on the wire. But OSC is tag, value. So you get a bundle of tags in the beginning, and then you get a bundle of values. But the values are aligned on 4-byte boundaries and things. From the tags, apart from block logs and strings, you can pre-compute exactly where in the string the stuff will be, and so you can encode it and decode it very rapidly. Also, you can't create nested data structures, and that's what's called simplicity by design. JSON and XML, you can create nested data structures, but you shouldn't have nested data structures in protocols, because then they're going to be so frigging complicated you can't understand them. By forcing this level of simplicity, at the top level you can send integers and floats and strings. If you can't blobs, if you can't design an interface using flat structured interface strings and integers, you should get another job. If you have to use JSON or something like that with 10,000 levels of indirection and stuff like that, I mean, forget it. Go boil the egg. Sorry, this is my prejudices coming out here. You don't like JSON. I mean, come on, you've got to know what packets. Why have you got to put tags into data? You're supposed to know what the data is. If you don't know what the data is, come on, you're sunk. Yeah, sorry. Can I have a beer now? Oh, good, thank you. Oh, yeah. The other thing I was going to say was, that's somebody else's, was back to the first problem. I learned something interesting. I implemented MTP. That's the fun to learn how it works. The network time protocol. And do you know how it works? It's really simple. It's very cool. You send. So, well, not quite true. The first version of the RFC, which is still implemented, is very simple. I think they're up to version 3 now. The latest version is totally unreadable. They've fucked it up since then. And So how it works is, here's your computer here, me, something like that, and here's an NTP server. This has a very accurate clock in it. It's Indian clock, so it knows really accurate time. And you send off a UDP packet at time t1, and it receives it at time t2, and it sends back another packet at time t3, and you receive it at time t4. That's all that happens, nothing else. So if you think about it, here's me, here's the first one. So let's assume my clock has got an error of k. Its clock is really accurate, my clock is bad. It's bad by a factor of k. So the real time I send it is t1 plus k. That's the time I send the packet. And if the delay over the network is delta, then the time it's received is t1 k plus delta, then that equals t2. So they measure the time and then receive it. And now if we send the packet back at time t3, then we should receive it at a time which is actually t3 plus delta, because it takes that long, and that's out by, yes, no, that's correct. No, but that clock's wrong, plus c. So now you've got two equations, t1 plus k plus delta is 2, and you assume that the back and forth propagation delays are the same. It's back and forth reasonable assumption you make. You've got two equations and four measurements. You can solve it for those, you solve it for that. So I thought, oh, that's fun. So I wrote a little ALEC program that did that. Boom, 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 boom to this server. And guess what? I think we've been banned from the clock server. I've got to find another entity server. And then I read somewhere in the spec, it said, if you do it more than once a minute, you'll be banned because it's I have lots of trouble testing software. You start implementing it, I've tested against that server. And suddenly it stops working. It's on my program software. Turns out you've been banned. So it's rather fun. So that we'll have to do in the because when we've got like hundreds of people in the audience, they'll all have their computers and all their clocks will be wrong. And so if I say play this note now, and all going to boom at the same time, if their clocks are all wrong, we'll hear it. So the first thing we'll have to do is adjust all the clocks. But we don't need to adjust them against NTP. Just write our own private version of NTP. Sorry, I meant to ask, who in the Erlang, is anybody in the Erlang group who does the clock here? Who does clocks? Clocks.
Parts of clocks.
Clock drift, NTP, clock sync.
Rika.
No, I have to go and ask. Because the part of the plan, well, the Sonic Pi, when it's distributed, actually has, it's quite a big thing, it's 42 megabytes, and it actually has Ruby and the Super Collider hidden in its belly, as it were. And it's going to have Erlang hidden in its belly as well, pretty soon, so we can do this and send it into distributed music. We want to make a kind of distributed music player that we can do distributed programming. Distributed music programming is the plan. Good fun. Yeah, thank you.
Otherwise, thank you again for the two speakers and the host. And don't forget to pick up the big article if you need. First come, first serve. Oh my god, I'm so far away.
Run. Just run.